Earth scientists study the four major spheres of Earth processes: the hydrosphere, which involves all water on Earth in solid, liquid, or vapor form; the biosphere, which involves all life on Earth; the geosphere, which involves the solid part of the Earth from its surface to its core; and the atmosphere, which involves the layer of gas that envelopes the Earth. Earth scientists study processes that occur in the intersection between the atmosphere, hydrosphere, biosphere, and geosphere. In this unit, we will focus on applications of functions, domains, and linear equations that Earth scientists use to understand and mitigate losses from powerful earthquakes.
The 2011 magnitude 9 Tohoku earthquake in Japan lasted 6 minutes, created tsunami waves that were reported to reach over 130 feet in height, killed thousands of people, and caused hundreds of billions of dollars in damage. But the results could have been much worse. When the earthquake occurred, alerts were sent out from an earthquake early warning system that caused automatic shutdowns of trains and utilities, alerted emergency response teams, and warned people to take emergency precautions before the damaging seismic waves reached them. Earthquakes and early warning systems, like the one used in Japan, are complex, but much of their basic operating principles can be understood by applying properties of linear equations.
Because of their destructive capabilities and mysterious origins, earthquakes have captivated people around the world for thousands of years. It has only been in the last 2 centuries that we have really begun to understand that earthquakes result from a rapid release of energy within the Earth that occurs when two sides of a fault, a crack inside the Earth, suddenly slide past one another. The energy stored in rocks that is released during earthquakes is built up primarily by the slow movement of the tectonic plates that make up the outer layer of the Earth.
The energy released during fault slip propagates through the Earth as seismic body waves known as P and S waves. P waves are longitudinal waves in which vibrations occur in the same direction as the waves propagate, whereas in S waves, also known as shear or transverse waves, vibrations occur perpendicular to the propagation direction. When these waves reach Earth's surface, they become surface waves, which travel more slowly but have much greater amplitudes. It is these surface waves whose large amplitude vibrations wreak the most devastation on the built environment.
Most earthquakes we feel at Earth's surface typically occur several kilometers beneath Earth's surface, which is the main reason they have remained so mysterious for millennia. It also means that scientists cannot directly observe them and instead must use indirect means to investigate them. The primary tool of the earthquake scientist is a seismometer, a sensitive instrument that records the vibrations that occur once its type of seismic waves arrives. Although their vibrations have by far the smallest amplitudes of all seismic waves, P waves travel through Earth the fastest and are the first to arrive at seismometers, whereas slower but larger amplitudes S waves arrives next, and the slowest but largest amplitude surface waves arrive last. The records that seismometers produce are called seismograms, and seismologists read these seismograms much like a doctor or nurse reads an electrocardiogram in order to determine the size, locations, and energy release during an earthquake.
There are a number of factors that control the speed at which seismic waves propagate in the Earth. The Earth is made up of a number of layers, each with different material properties, and we know about these layers thanks largely to seismologists. The speed at which seismic waves propagate is governed by the mechanical properties of the materials they travel through. Luckily, the damage associated with earthquakes is usually very near the earthquake source, so when evaluating earthquake hazards, seismologists usually only have to consider the rate at which seismic waves travel directly through Earth's crust parallel to the surface. The time it takes for a seismic wave to travel from the epicenter, the point on Earth's surface above the earthquake source, to another point on Earth's surface is linearly proportional to the corresponding wave speed and the distance it has to travel. Seismologists can determine this time by constructing a linear equation in the form of y equals m times x, where y is the distance from the epicenter in kilometers, m is the wave speed, and x is the time in seconds. Because S waves travel slower than P waves, they arrive at seismometers after P waves, and the slope, m, of the equation is smaller for S waves. Graphically, these relationships can be viewed on a travel time diagram. Note that, with increasing time and distance, the spread between the S and P wave curves increases. Therefore, by simply measuring the difference between the S and P wave arrival times, shown by the curve labeled SP, seismologists can compute the distance the seismometer is from the epicenter.
Seismologists now understand a tremendous amount about earthquakes. They can locate them to very high precision, compute the energy released, identify foreshocks and aftershocks, and even build computer models that accurately simulate earthquake rupture propagations. So incredibly complex, and we don't have a direct view of the faults on which earthquakes occur. We cannot yet predict earthquakes with precisions of hours, days, or even years. While scientists continue to make strides in the directions of earthquake predictability, seismologists have focused more recently on developing earthquake early warning systems.
Earthquake early warning systems work on the same simple principle that while P waves are faster than S waves and S waves are faster than surface waves, information sent through communication systems is nearly instantaneous. If computers can estimate the energy being released by looking at the P waves of an earthquake, they can warn surrounding areas of the impending surface waves tens of seconds or even minutes before they arrive.
My name is Anne-Marie Balte. I'm a seismologist at the United States Geological Survey, USGS. The ground shaking at your location is simply a linear combination of two components. So that's magnitude and distance. So a larger earthquake will cause more ground shaking at your location, and a smaller earthquake will cause less ground shaking. The closer you are to an earthquake, the more ground shaking you feel. The USGS Shake Alert Earthquake Early Warning aims to alert people if they are going to feel ground shaking at their location. So we model that ground shaking as a combination of the magnitude and distance to determine which populations or which areas, which locations are going to feel ground shaking. Alerts are delivered by two main mechanisms. The first is wireless emergency alerts, WEA, which go directly to your cell phone. In California, you can expect to receive a wireless emergency alert, just like an Amber Alert. The second mechanism is through third-party apps, where you have a little more control over saying which earthquake magnitudes, how much shaking you want to be warned for. Regardless, if you receive an earthquake early warning alert, or you feel ground shaking, we recommend that you take protective action. Stop what you're doing, drop to the floor, look for a place to cover, such as under a desk or a table, and then hold on to the leg of that desk or table. Shaking is coming. Take a moment right now to look around where you are. If you received an alert at this moment or felt earthquake shaking, where would you drop cover and hold on? In this manner, earthquake early warning aims to alert people before the shaking comes so they have time to drop cover and hold on, and thus mitigate or reduce the number of injuries due to earthquakes.